Now, this week we will be talking about the p-type controller. If I'm not wrong, last week we did look at the symbolic toolbox. We did some simulation on the root locus, on the boulder graph, and also we've talked about how to calculate the step response, ramp response, and impulse response. Now, this week we will utilize the root locus method. We will talk about the p-type controller. And today's topic is all about the controller design. We have some requirements. Actually, we have only one requirement, that being the settling time. So what we will be doing today is the following. We will be looking for p-type controllers. We will have this open loop system, as you can see. And we want to have such a closed loop that the closed loop step response takes only 4 seconds, or 2.5, or 1.5 in D, seconds to get out of its transients. So we will be trying to tune the transients of the closed loop. Now, there's also something different in C, where you can see we have a critically damped requirement for the closed loop. So now we've talked about the p-type controller last week. This is the most basic controller that you can find. And since it's just a static gain, we're trying to calculate this gain. And we've also talked about a first order system, second order system, but we have a third order system here. So before we go into the whole design step here, I have to talk about the settling time and the time domain transient properties of a transfer function. So, for example, if we have a certain system, let's have 1 divided by s plus 1, I need to be able to associate the poles and zeros of a transfer function to the transients of a step response. So, of course, we're using the S domain, which does not directly tell us about the transients of the system, but I can study the poles and the zeros of a system, and it is not really that hard to get some conclusion about the transfer function. Now, for example, if we have a first order system, as given in line 3, what can we talk about this system? What can we tell about the system, especially about the step response? Before I use the symbolic toolbox, let me define it in the control system toolbox, which is basically the same, but I can use step on it. I can use the step function. So, yeah, how can I determine the transients of such a system? For example, I know that if I call the step function on this transfer function, what I will get is, I will get, for example, 0 overshoot. Because it has a real pole, I can directly conclude that this will not have overshoot. And I can also tell that this will have 4 seconds, roughly, of transients. So the settling time would be 4 seconds. And why and how I can conclude this is based on the fact that, let me go back to this one here. Let me define S. It's based on the fact that we are using the Laplace transform. So what I can do is I can go ahead and look for the Laplace domain representation of the response, because the transfer function is basically the relation between the input and output. If I know the input, which is a unit step in this case, if I know the transfer function, I know that the multiplication will give me the output in the Laplace domain. What I can then do is I can take the inverse Laplace, so I Laplace in this case, of this multiplication. So what is U in our case, if we are talking about the unit step input? It's 1 divided by S. Because any constant, its Laplace transform gives us 1 divided by S. So I can basically go ahead and take this and pass it to the inverse Laplace. So that would look like this, and this should give me yt because it's the inverse Laplace transform. Let's see. Now, this is the time domain representation of the response. And what I can see is I have an e term with the power of minus t, and this is it. So this is also the reason why I conclude that there will be no overshoot, because the gain of this for any t does not equal to a bigger value than 1. So its absolute value is at max 1, and it is decreasing, by the way. So since this is 1 minus e to the power of minus t, as t increases, this term decreases and it will settle down to 1. So therefore, I can see that this is basically a zero overshoot response, and I know when e to the power of minus t decays. If we have the time constant 1, it's tau, so 5 times or 4 times tau, depending on the precision you want. This will decay. And the definition of the settling time is that we have a value in the steady state, and we look for the time instant where the response does not leave the 2% band on it. So 1.02 times YSS, which is the steady state value, or 0.98. So this is a 2% band here. We are looking for the first time instance where we enter this band and don't leave it. So that's basically the definition of the settling time. Yeah, if I have a more general form, for example, let's have a pole here. Let's define it. And since this is a first order system and we're working with real valued coefficients for our transfer functions, we know that p should be real. It cannot be an imaginary value because, or a complex number, because the coefficients would be then complex. So therefore, we have p, which should be also defined real. And that's basically it. Now, you can pass 2 additional arguments here, which tell the inverse Laplace transform function I Laplace what the Laplace domain variable is and what the time domain variable will be. Somewhere here, where is it? You can see that you can basically define it, or you can also omit it. I'm quite not sure. There we go. It also works like this. Now I can see that the constant term is 1 divided by p, and then we have e to the power of minus p times t divided by p. So again, there's a time constant, and I can see immediately that it takes 4 times the time constant to have a settling time. So what I can basically conclude is I can say that generally it would be equal to 4 divided by p because of the e term here. So for first order systems, I can say that there will be zero overshoot because we are on the real axis. Therefore, the e term here would be a real value, and therefore there will be no oscillation whatsoever. And hence, I can say that this will not overshoot. For real pole systems, there will be zero overshoot. The settling time here is determined based on the time constant of E. And for the first order system, we can use 4 divided by P or 5 divided by P based on the precision. Now, what about, for example, second order transfer functions? Because this is just the first order version. What about higher orders, like the second order? So for the second order systems, we would have a polynomial that would look like this. And this equation would give me the poles of the system. And we all know that you would use something called the discriminant that is calculated by using b squared minus 4 times a times c. And based on this parameter, the discriminant here, I can determine whether I would have real poles, whether I would have poles that coincide, or if I have complex conjugate values here. So this determines the characteristic of that. And based on the characteristics, I can also conclude what the step response would look like about the transients, especially, because in steady state, it doesn't matter. In steady state, we will have just a static gain because this is a linear system, the transients are gone, and it would be just a gain. So, yeah, the solution here is important. For example, I know for now that if this is a real valued polynomial, if all the poles or both of them are real values, there will be zero overshoot, for example. In order to determine if a system has a certain behavior, we will not use this, but it will be based on this, not ABC or b squared minus 4ac. That will not be the thing that you will see. Instead, what you will see is you will see the following: s squared plus 2 times zeta times omega n times s plus omega n squared. And yeah, the thing that we've done here is we've divided by a, and you can see that the sum of the poles appear as b divided by a, and then we will have c divided by a. So the sum of the poles and then the multiplication of the poles, which is familiar, I think. And we've called them some special parameters like zeta and omega. Now, if we focus on the solution of this polynomial here, let's skip this part here. We first need the discriminant again. And that would be b squared, which is this, minus 4 times a is equal to 1, c, which is this. So if we work our way, the following equation will show up. Now, here we have also common terms. So 4 omega n squared is the common term here. So therefore, we would have zeta squared minus 1. Of course, for the exact solution, we need minus b, which is minus 2 times zeta omega n, and then plus or minus the square root of the discriminant, which is basically this stuff here, divided by 2a, where a is 1, so divide by 2. So let's divide by 2. And I can also get rid of this 4 because square root of 4 is equal to 2, and then it's gone. So we can also see that I can directly take this omega n squared out, because by definition omega n is a natural frequency, therefore it's always positive. So we have omega n here. Now there's just one parenthesis too much. So there we go. That's basically the solution of a second-order polynomial, which has the coefficients given in line 3. So this may not look that special or important, but hang on. We can, for example, see that the discriminant gives us an option based on the zeta squared here. And we can use zeta in order to determine if it's a all real solution, if it's a complex conjugate solution. So zeta here basically is used to see what the poles will look like. For example, if we have zeta squared minus 1 positive, so zeta is greater than 1, then the solution becomes real. Therefore, we have 2 distinct real poles. If zeta is equal to exactly 1, then this term here vanishes. This goes to 0. Then we have the same pole twice, which will look like this. And if zeta is less than 1, and positive by definition, then we will have the following. In order to come up with a solution, since zeta is less than 1, this means that this term is negative. Let's have the negative separated here. So this would then end up in 1 minus zeta squared, which is a positive value, and then we would have minus 1, which is actually I or j here. And we can see that the imaginary part then, let me put the I here, you can see that this would be then the imaginary part of the poles, and then we would have the real part here. Now, this is basically the solution that we will be mostly working on because we have complex conjugates. If you want to have certain overshoot, then you have to have this solution here. If you want to have zero overshoot solutions, then you would pick zeta bigger than 1 or a zeta exactly equal to 1. But in these cases, we don't have really a formula for the settling time. Our settling time formula that I'm going to introduce to you is basically defined for such systems here. And as far as I know, I'm not 100% certain about this, but in the textbooks, I've seen that it is not valid for 1, but 0.7. So there should be a certain damping ratio. By the way, let's name also our parameters. Zeta here is the damping coefficient. So it calculates how much damping the system has. And omega n is the natural frequency. And this one here, since it includes the zeta here, which is the damping coefficient, we have the natural frequency, the damping coefficient combined gives us damping frequency. So, and then we call also this part here sigma, which is basically the real value of the solution here. And yeah, for example, if we have such a system, we have a formula that helps us to determine what the settling time would be equal to. And this is the formula that we have. There's a proof for this in the textbooks. You can look it up. Now, if you have the zeta and omega n values of the poles, of the complex conjugate poles, then you can use the real part of it to determine what the settling time would be. There's also a formula, and I'm going to give you the inverse formula for now, which looks like this. The square root of pi squared overshoot squared, where you can use a certain overshoot value in order to come up with a damping coefficient. So there is a correlation between settling time and overshoot, and we can use these two equations here in order to choose, for example, poles on the S domain, or if we have the poles, in order to determine what the step response would look like, or the transients of it. There are also peak time, delay time, and rise time formulas, but I'm not going to focus on them today. But there are certain formulas that all use zeta omega n. So therefore, it is really important for us to have these parameters and to know what they mean and how we can use them. And I'll also show you where zeta and omega n would arise basically on the S domain. So if we have a certain criteria, as we have here, for example, 4 seconds of settling time, then what we can do is we can use this formula here in order to come up with a zeta omega n multiplication in this case. If we would have had another requirement like the overshoot, then we would be able to calculate what zeta and omega n should be exactly equal to. So now, it's also important to note that other than these formulas, we also, since this is S1 and 2 is equal to this, it is also important to look at certain properties of the solution. For example, if you take the absolute value of this just for one pole, then what we have to do is we have to take the real part, take the square of it, plus the square of the imaginary part here, and then also the square root of this. Now, let's see what the result is going to be. Now we have zeta squared omega n squared plus omega n squared and then 1 minus zeta squared. This would give the following. Again, we have this term here. We have omega n squared and then minus omega n squared zeta squared. So these cancel out, this one and this one basically. And we are left with omega n squared. Since there's also a square root on this, we get omega n. So the absolute value of s is equal to omega n. So if we're on the s domain, the x-axis is the real part, and then the y-axis is the imaginary part. Then, if you have the absolute value of s equal to omega n, what would that look like? Because this has a special geometric interpretation. S equals omega n. Now, for a plus bi, and the absolute value of this, we would get the following. We would have a squared plus b squared and then the square root of this. And that would be equal to omega n, or in other words, if I take the square, I'd get a squared plus b squared equals omega n squared, or let's call them x and y. Do you know what this is? This is basically a circle. The center is the origin, 0, 0, and the radius is omega n. That tells us the following. If you have a certain omega n value, if this is fixed, then you're basically moving on a circle on the s domain. And the radius is basically the natural frequency omega n, and that's it. What we can also do or look at is the argument of s, which is basically the inverse tangent, the a-tan of the imaginary part divided by the real part. This is the imaginary part, and we divide it into the real part here. There we go. Now, what you can see here is now that the omega n cancels. So it's not really depending on omega n, but it depends on zeta. And looks like this. Now, this has also a special meaning. If you have, for example, a fixed damping ratio, zeta, then you would end up in a fixed inverse tangent, which would give us the angle here. So there's this fixed angle, and that is basically represented by a line. So if we're moving on a fixed zeta value, then we're moving on a line. If you have fixed omega n, we're moving on a circle. And if we combine them, we have basically a intersection point that gives us this exact solution here. Now, and why is this all relevant? Because we know the settling time, overshoot, peak time, all the transients about this system. We know the second order all-pole transfer function so well that we will use it over and over again in order to design controllers. The second order transfer function is crucial to us. And therefore, we will use zeta and omega n to come up with zeta omega n is basically the most important part that we will have to overcome. Once that's done, we're pretty much done. Now, the second order transfer function is important, and as you can see here, we don't have a second order transfer function, and that's not always the case. Most of the time, you would not have a second order transfer function. So what should we do then? Well, basically, the solution that we are interested in throughout this course most of the time is the solution that would converge to this second order transfer function. In order to have this convergence, what we will do is we will have a part that corresponds to this exact second order part, and then all the other poles and zeros. And the best way that we can do for now to deal with this other poles and zeros is to push them far away. So we're basically trying to convert all the systems that we will control into second order all pole systems. And this is called dominant pole placement because the dominance of the system, or the behavior that should be dominating in our control strategy, is the second order part. Even though we have a third order system, we want to have two poles according to the formulas, according to zeta and omega n, and then the third pole should be placed far away, if it's possible. Because in the upcoming weeks, we will see that this is a good strategy. If you have only the second order part to be dominant and the other non-dominant parts are pushed away, that is a good control strategy. So, how can we achieve this, basically? Let's try to look at today's design problem. Let me first define the system. These are the poles. Now we have three poles, and our settling time criteria is Ts equals 4. Now the first step is to determine zeta and omega n. We have to know what zeta and omega n is. Now therefore we have the following formula. Zeta omega n. And that's basically it. So we don't have any additional information about the closed loop that we're looking for. So this means that we don't have that much to work with because we have only the multiplication of zeta and omega n. Let's also write down our second order polynomial that we will use over and over again. So this was the polynomial. And the only thing that we know, or the only thing that this gives us, is that the zeta times omega n multiplication should be equal to 1. Now we're a bit lucky because we have this multiplication here. So it is valuable because if we would have known what omega n, what zeta would be, then the only unknown would be left as omega n. But still, if we have the multiplication, that also works because we get rid of this and there will be no zeta in this polynomial, which means that we have accomplished half of it because we know the value of this coefficient at least. So let's also look at our controller because we're trying to design a p-type controller. What we have to do is we have to look at the following. We have this control loop that I'm drawing most of the time that looks like this. That looks like this. And we're choosing the p-type controller. Let's represent it with a k. And we're looking for the closed loop. So in order to calculate what the closed loop looks like, we need the following formula, k times GSS. We've used this last week as far as I remember, 1 plus k times GSS. Now, we have to look at our controller and the closed loop that results with the controller. And we have to look at our ideal closed loop model, and we need to try to match them. Because all that we have for now is this polynomial. and the polynomial or the characteristic polynomial that will come from here. So we can extract the numerator and denominator using this numdan function. And then we're almost done. So let's see. And we didn't define k. Since I know that this is basically a real value, let me just quickly still. Yeah, this part here. And this part here. And I guess omega n is also not defined. So let's do that too. Omega n is also real, so I can zeta. Oh yeah. Let me just get rid of this. There we go. Now, first of all, our open loop polynomial is s cubed plus 13s squared plus 40s, because we have a pole at the origin, namely this one here. We have 0 here. But since we're using a p-type controller and we have a feedback structure, we end up in this characteristic polynomial. So the choice of controller would manipulate the characteristic polynomial as shown here. The only thing that we're choosing or changing here is basically the constant term of the polynomial. So there's a bit of a challenge because we have 3 poles. This is a third order polynomial. And the only thing in the polynomial that we can change is basically k. So we're pretty much limited to k, and we're pretty much limited to the fact that we are only changing the constant term. Yeah, and all the other terms are not affected by the controller. So if I'm going to come up with a polynomial that should model the ideal closed loop, then the coefficients should look like this. I don't care about the constant term because I can change it, but all this part here is fixed. If you, for example, try to come up with a controller that chooses a characteristic polynomial that looks like this, etc., this is not possible because you have already 13s squared, and no matter what k is, it will not change. It will always be 13s squared. So therefore, this limitation here is pretty important, and we'll see why. And from the design point of view, I only know, let me also include this one here. I only know that the zeta times omega n multiplication should be equal to 1. So I have this equation here. So what I can do is I can directly plug in 1 into this part here. There's also 2 times here. So I can directly plug in zeta times omega n. But what I'd like to do is I'd like to define zeta equals 1 divided by omega n. So to remind myself that I'm basically choosing zeta in terms of omega n. So if I plug in zeta 1 divided by omega n, I'll get 1 instead of the multiplication here. And then I will have 2s plus omega n squared. And that's it. Now, of course, if that's the case, even in that case, I'll see that using only this polynomial, I cannot achieve this polynomial because this is a third order polynomial and I have only a second order polynomial written down. And my settling time, overshoot, peak time, whatever formula I have, only works for such systems, such polynomials. I can only determine the settling time, overshoot, etc. of this polynomial. But what I have is this. So in order to be able to choose certain controller, I have to add another pole in order to match the degrees of the polynomials. And then I'll take all the coefficients of the terms and I will equate them to each other. And if I solve that, I'll get my controller. Also the details of my solution, if it's possible. So basically, the step here is to define another pole, because it's a third order one and I only decide on 2 of them. And hopefully, the only thing that I can do is to hope that P should be positive. And why do I need that? Well, basically, if zeta and omega n is positive, then I'll get stable poles here. Poles that are on the left half plane in the S domain. So that's no problem for me. If I choose zeta and omega n, that's okay. It should be positive, zeta and omega n, and I'm good to go. But if I add another pole, S plus P, another polynomial part, then I'm not really sure about that, because if I have a certain P, my pole will be at minus P. And if P is positive, then this will be on the left half plane. Since I'll multiply PES and PDS, I'll get stable poles. But if that's not the case, then I will have an unstable closed loop, no matter what zeta and omega n is. So I should be really careful here. Since this is a third order system, that's manageable. But if I have higher order systems, there will be more poles. And all of them should be on the left half plane if I'm trying to design a feedback loop, because it should be stable, and then the transients should be defined by whatever requirements I have. So therefore, this needs a little bit of attention, but my ideal polynomial, or my polynomial that I want to achieve here, is basically PDS times PES. So let's look at that. So we have this, and then we have also this here. So somehow, these two here, yeah, these two should be equal, or should share the same poles. So since I have S cube here, if I calculate this, if I expand it, I will see that I will have S cube, and this is also S cube. I can directly use the coefficients to equate them. If that's not the case, I have to normalize, or I have to turn one of the polynomials into a monomial, and then I should equate the coefficients. So let me expand the pole here, and maybe also use VPA here. And then the denominator. So there we go. S cubes are equal, they have the same coefficient, but the coefficient of S squared is 2 plus P in this case. That should be equal to 13. And then 40S should be equal to the sum of the coefficients of S, and so on and so forth. So instead of doing this manually, what I can do is I can use the symbolic toolbox. We have a command, coefs, which you should be familiar with. And I can use this code here that defines that we have an expression that should be a polynomial. We have the S term as the polynomial variable, and we want all the coefficients, even though if there are some of them equal to 0. And then I want also the coefficients of the denominator, because that will have the controller parameter. So there are 2 sides to this. One of them is the controller closed loop characteristic polynomial. The other one is the one that I construct in order to choose the transients, choose the behavior. And so, yeah. Now we have the problem here. What I can do is I can loop through each of this. And the reason why this works in MATLAB is the fact that if you use vectors and then some operations on them, then MATLAB tries to do it by element. And if that's possible, it'll just carry on. Therefore, we will have a vector here, vector there. And if I have the equals operator here, then element by element would be the comparison here. So therefore, I have a vector of equalities in this case. So I can then print them. So So let me also use VPA 4 and also display maybe in order to have nice equations here. So now, what did I do? Basically, I have defined the system in the symbolic toolbox. I have defined my requirement. I have defined omega n as a symbolic variable, which is real and should be positive. I have chosen zeta equals 1 divided by omega n because of the fact that the settling time is equal to 4. What you can do basically is also to use it this way. 4 divided by ts times omega n should also work. Should be a divided by. Instead of having this manually, you should always use this strategy here, because if I update ts, then this should also be updated and everything will be up to date. So I have chosen zeta according to the formula in terms of omega n and ts. And then I have this desired polynomial here. I needed to add another polynomial, the residue polynomial, because of the fact that this is a second order one and my closed loop is a third order polynomial. I also calculated what the closed loop with the controller and the feedback would be, and I took all the coefficients, equated them to each other, or compared them, and I'm just printing out the whole problem. That looks like this. Now, the first equation here is a trivial one, but this is also necessary because this is the highest order term coefficient. If this is not equal to each other, then I'm not able to calculate this. If, for example, this is 1 equals 10, this means that the coefficients on the right-hand side should be divided into 10 in order to have S cubed here. So, and then we have p plus 2 equals 13, which means that p should be equal to 11, which also means that p is positive and I will have a stable closed loop. And then I can use 11, which makes 22, and then 40 minus 22, 18. Square root of 18 is my natural frequency. And 18 times 11, 198, gives me the controller coefficient that is necessary to assign the poles that I've chosen here. Of course, I'm not going to, again, solve them manually. What I can do is I can use solve here. That should practically create me the solution that I've already talked about. Now, of course, since I have omega n squared in the equations here, and the symbolic toolbox does not know if it's a positive value or not, the only thing that I've told the symbolic toolbox is that omega n is real. Therefore, there will not be a unique solution, there will be a symmetric solution. Let's see what it is. So you can see there are two solutions. And since this is a struct and I've saved it in the variable sol, what I can do is I can use the dot operator to access each field. So sol.k gives me the k values. Sol.p gives me the p values and also the omega n values. Now you can see that the p values and k values are basically identical, but we have some symmetry in the square roots here. Now, I've talked about the omega n being positive by definition. Therefore, because negative natural frequency does not make much sense, therefore, I'm going to eliminate this negative solution here, and I will be focusing on a positive one. So therefore, in order to do that in MATLAB, there's an easy way. What I can do is before I do that, let me define all of them into a parameter. So I'm using placeholders. I've talked about this. If I have a k value, I will call it a k val because I want to preserve the symbolic variables here. So if I have p, I will define a new variable called p val, and so on and so forth. Now we have k val, or let's have omega n val. Let's see if it works. So there we go. Now, in order to choose some elements, what I can do is I can just directly give my condition here. Now, if I have such a condition, I will get, of course, this. In order to prevent this, I should maybe change everything into double, because I'm still in the symbolic toolbox. I have symbolic expressions. But I can get rid of the symbolicness here by using the double function here, which converts it to numerical data, because I need numerical data at this point. Because I've defined my problem, I've defined my feedback structure, I've calculated the necessary conditions, and I solved it. At this point, I have just numerical data. And therefore, I need to convert them into numerical data. So once that's out of the way, I have a logical array. Now, this will help me in determining which elements of the vector are satisfying my condition. Therefore, I can store this in a variable and use this variable as an index to access the ones that are satisfying my conditions. Of course, this is called omega n val. There we go. Now, before that, I had and val two values. This is a vector. I eliminate based on the positiveness of the value. So therefore, I got the positive value here. I can apply this index to all of them to get rid of all the unnecessary results here. So k-val should be equal to k-val of these indices, and then we will have p-val, which should also eliminate that, and then omega n-val, and there we go. So now I should have only the solution that I'm interested in. And there we go. My pole is at -11, my frequency is this, and then I've also the p-type controller, which is 198, and that's it. Now, at this point, you may say that I'm basically done, we've finished, we've designed the p-type controller, and that's it. Unfortunately, it's not. If you have a certain design, then you should verify if the design really works. Our assumption was that the requirement is equal to 4, so the settling time should be in the closed loop equal to 4. We have to use the controller, use the transfer function, calculate the closed loop, apply a step type input to it, and see what the transient looks like. Therefore, since we have the controller here, what we can do is we can basically use the feedback command here, and then use k-val times gs. Of course, I need to define also gs here. So let's define that. 1 divided by something. Now there are two ways I can directly calculate this here and then provide the coefficients, or I could ask MATLAB to calculate them for me by using the convolution operator here. I can basically give all the poles. 1, 0 is the pole at the origin. 1, 5 is s plus 5, and then 1, 8 is s plus 8. And this would calculate me the transfer function like this. And if you look closer, you'll get 0, 8, and 5 as the poles. So I've defined my transfer function using the symbolic toolbox here and the control system toolbox here, because the verification step will be using GS here, not GSS. So I'm basically calculating the closed loop. Now let's see what the closed loop looks like. And it looks like this. Now, you might remember that the first part was exactly this, and then we had plus k. Now k is 198, so this is expected. Now I still need to apply the step response on it. So let me just create a figure in order to, let's have all the stuff written now. Now let me calculate it and plot it manually. Plot t, y, then line width. That's it. Now I can use also step info, which gives me the information that I'm basically looking for. And it can calculate the overshoot, the settling time, etc. So let's see how it looks like. Now, there we go. Now, this is a certain step response, but I can see that at 4 seconds, I'm approximately at the transients because the oscillations are damped out. And here it sort of enters the band that it should. And the step info function here shows me that the settling time here is 3.957. So interesting, because it is almost 4. And based on the fact that we have basically, not this one here, maybe this one here, we have basically such a closed loop transfer function. And I can see that this part is probably the part that I've designed, which is PDS. And this part was to equate the orders of polynomials, but it seems to be working. Since omega n is square root of 18, omega n squared is 18. So yeah. Now, what I can do is, since I know that omega n val is a certain value, and I know that due to the settling time requirements, we had the zeta omega n multiplication equals 1. So let me pull this equation here to calculate zeta. So let's run again and again. Now zeta val is equal to that, which is not really what I'm looking for. So omega n val. So omega n val, zeta val. There we go. Now, since omega n val is 4.24 and the multiplication should be equal to 1, we have 0.2357 as zeta. And since this is basically the damping coefficient, or the damping ratio, basically, and since this is closer to 0, I can see that there's not that much friction going on. Therefore, I would have oscillations like this. If zeta increases, then all the oscillations will decrease. So, which tells me directly that if zeta is a high value, I will have low overshoot because there are less oscillations in the response. Therefore, this is expected. I have met the criteria, settling time equals 4, but my zeta value is a bit low. Therefore, I have high oscillations. But I don't have that much control over it because if I want to have the settling time, then there's just one solution and I've calculated it. There's only one solution and I've already calculated it. So therefore, there's not much to do here. I have to stick to this solution. Now, interestingly enough, this p-val here is at 11 and my poles look like the following. Let me go ahead and do the following. Let me create a subplot here to have a side-by-side view. And let's call it this one here and the next one. So let's also have a root locus here in order to see what the open loop was and how we could have basically designed the controller. There we go. Now, before I continue, I might do the following. Since the root locus plot is basically a plot where k varies and I have done the poles moving. So I already know what k I've chosen. So I could also calculate all the poles and zeros in the closed loop. And I could place them on top of this root locus so I can see where I've chosen my solution. So therefore, I can basically use PZ map here. That would give me directly the poles and the zeros. And I provide the closed loop here. So now I want to plot the poles. So the real part of C poles versus the imaginary part of the C poles. And let's place in some crosses with line width 2. Of course, I could also say that this is AX2. Now, let's see. Hopefully. There we go. Let's basically have it like this. So if we plot the root locus of the open loop, GS, we get this root locus plot. And we have one pole at the origin, one pole at -5, and the other one is at -8. So what we can see is that as k increases, one of the branches goes this way and the other one is symmetric. And then we have also a third pole which goes to the left. Now, this is a good strategy. This is a good root locus because of our strategy, because of the fact that we have only the second-order part here to choose, and we want them to dominate this behavior. And luckily enough, two poles are in this vicinity, and one of them is approaching to negative infinity, or it just goes further and further away from these two poles. But there's also a risk that we might touch j omega here, which is basically the marginal stability boundary. Therefore, I might end up in unstable solutions. But there's a certain point, for example, the settling time value at this point here that we've already designed, that seems to be working, because our strategy was to have two poles dominant and one of them non-dominant and far away. So this works here because the root locus also moves in that way. So let us also look for the zeta and omega n values. So since I have zeta and omega n, I can draw a special grid here, which is called the S grid here. This is basically the complex grid that I'm looking for. And let me also show you the help here, help S grid. You can see now that we have the argument 1 equals zeta, and the second argument is omega n. So I can provide some zeta and omega n values and see how they look like on the S domain. So let's have zeta val and omega n val. So there we go. Now let me zoom in a little bit. So hope that you can see it, but there's a circle here that has this radius 4.24. And then there's a line, and there are two lines basically symmetrically. And there's a value called 0.236. So one of them is zeta and the other one is omega n. And my choice here was to have the multiplication equal to 1. So I was looking for a circle that is basically growing with omega n. And I had a certain zeta value that would change the angle of it. And the intersection is the exact point that I'm looking for. Now, of course, I was not directly choosing zeta, nor I was choosing omega n, but I've chosen the multiplication of it. So maybe we can also draw a line that represents all the same points, or all the points that has the same settling time, So in order to do that, I need to recognize the formula. And I should see that this part is basically sigma, or the real part. So if I'm choosing a certain settling time, I'm not choosing a certain settling time, I'm choosing a certain real value for the poles. Since I will have complex conjugate poles, I'm choosing the real value for them. So this is basically 4 divided by TS. If I draw a line at 4 divided by TS on the S domain, that line represents all the poles that end up with the same settling time. So I've talked about zeta and omega n. One of them is a circle, one of them is a line. This one is basically the following line. So let's plot. I know what the x value here is, 4 divided by TS. So 4 divided by TS. And you can use ylim in order to calculate the current axes here, or the values here. So you can directly use ylim in order to plot some lines. Let's have a line, black line. Well, let's have a red line. So since I have a scalar value here, and this will have a 1/2 size, let me also multiply it with 1/2. So this will give me basically a vector with the same size, and then I can use plot here. Of course, this is a negative value because zeta times omega n minus zeta times omega n is on the left half plane. So there we go. Let me again zoom in a little bit. You can see that I was looking for the exact point where the omega n circle and the zeta line coincided, but that point was on this line. So not for a system, but for maybe other systems, I might end up in a different position on this line, but I will still get the same settling time. The only problem would be about this position of the third pole here. If this will become close, or it will come closer and closer, then even though I'm on this line, I would get a different settling time, because my requirement here is to have a certain distance at least. Now, this code basically takes in the settling time and comes up with a controller, and it also has some neat properties like showing the settling timeline, showing the zeta and omega n lines. That was basically A. So let me also quickly get rid of B, and then let's have a break. So in B, instead of having a settling time equal to 4, we have to change the settling time to 2.5. So we will have a faster transient behavior, because a lesser settling time means that it takes less time to achieve the steady state. Now, that's basically it, because I've already written the code in such a way that it adapts automatically. It uses this TS in order to come up with the zeta value. It constructs me the desired polynomial and then a residue polynomial. Since the system didn't change, all this part should stay the same. I'll see the problem, and then it will solve it, get rid of stuff, and show me all the results here. So let me run again. So there we go. Let me zoom in a little bit. Now, first of all, we can observe that we have almost no oscillation at all. We have just one overshoot and then a slight undershoot maybe here, and then it settles down. So I can directly conclude from this step response that zeta did increase. And I can also see that it did increase because the value was 0.23 something, and it is 0.544. So zeta did increase. But since the multiplication was fixed to 1 divided by 2.5, we have omega n 2.94. Now, the interesting part here is that this pole here actually is not that far away. It was on -11, now it is on 9 point something. Let's see what p-val is. 9.8. So it seems like the distance between the dominant poles here, the real value of the dominant poles, and the third pole did decrease. So in order to be able to show, what we can do is we can use the following. We know that the zeta times, or zeta val times omega n val gives us the real value of the dominant poles. And then we have also p-val. So the ratio between p-val and zeta omega n multiplication should give me a rough idea about the distance between them. I can determine this So let's display this string m, and let me copy and paste it here. So if I run this, yeah, p-val zeta val. So m is equal to 11. If I have settling time equals 4, I will have 11. So what about run 2? 6.125. So there's a massive decrease here. And I can also see that the settling time is a bit different than what I should expect, because the requirement was 2.5, but all I get is 2.0897. So this is basically showing me that my solution is almost good, is a better solution, etc. I can directly tell you that this solution with settling time 4 has a better dominance factor, or sticks more to the dominant behavior, but this one deviates a little bit because we have a lesser dominance factor. It's not far enough. We couldn't place P far enough in order to have a better accuracy. But it's still okay because of the fact that 2.5 and 2 are at least in some range. It could have been worse. So yeah. What else did change? Well, basically, we have a lesser k-val. So it was 198. Now we have roughly 85. So it's a lesser k-val. And on this root locus, for this system especially, the lesser k-val means lesser zeta value, because of the fact that if I've chosen some place like this, it was 198. So around here somewhere, if I choose it here, I will have lesser zeta value because it's correlating with the cosine of this angle here. So if the angle increases, the cosine decreases, therefore zeta decreases, therefore overshoot increases. So hope that you get the idea that if I look at the poles, if I look at the S grid, the S domain here, all I have to do is I have to get to know zeta and omega n, their meaning, and how if I change that, the root locus changes, and suddenly I can analyze the system a little bit better. And if I'm going to be a designer, then this is crucial, because if I can comment on the system, the more I can, the better I can design my controller. So let's have a little break. And after the break, we will be continuing on C and D. And since I have a basic code, it will not take that much long to adapt this code and look at the upcoming tasks. So let's have a 5-minute break. So at 45, we can continue basically. Okay, let's continue on our discussion. The third task today is to design a closed loop such that if we apply a step response to the closed loop, it will be critically damped, which basically translates to zero overshoot. So let's copy this. Let's have 3. Now, at the beginning of today's discussion, we've talked about a first order system, that first order system for any stable P, for example, has zero overshoot. And then we've talked about S squared plus 2 times omega n S plus omega n squared. And if zeta is equal to 1, then that has basically the same poles on the real axis. So they coincide there. Now, our design requirement here is basically, instead of using 4 divided by Ts times omega n, instead of providing you with a settling time, we have just zeta equals 1. And that's the only change that I'm going to apply to this code, because that's only what I have to do. Now, this translates into the following. If you have zeta equals 1, you can see that this is basically not s squared plus 2 times omega n times s plus omega n squared. This is s plus omega n squared. So the solution should be s equals minus omega n twice. And that's it. Yeah, therefore, we will have, again, the solution here. Let's see what the solution is. Here we have zeta val. Here, that should also be equal to 1. And then we can see that we have a problem here. In order to see what the problem really is, let me comment this part out. So, for once we have these set of equations here. Now, 1 is equal to 1, and then p plus 2 omega n, etc. So if we look into the solution, we have, again, two solutions, sol.k, sol.p, and then sol.omega n. Now, we can see that both omega n values are positive, and here we did look for the positivity of omega n. And since this is satisfied for all the possible solutions, we have basically two solutions here. But this doesn't mean that both of them are meaningful for us or are usable, because of the fact that you can see that p is equal to minus a third and then also equal to 9. So we don't prefer this negative one because this is a unstable closed loop. And in terms of coding or in terms of a program that is used for design, we didn't look for the positivity of p because that's important. If we have an unstable closed loop, it doesn't mean anything to have a certain settling time or to have it critically damped. So therefore, what we should really do is we should copy this part and we should check for the positivity of p-val. Now, here I'm looking for positive omega n values. I'm getting rid of the symmetric negative ones. Here, I'm looking for stable closed loop. Because if I have zeta and omega n, if they match the definition, then the only thing that'll decide if the closed loop is stable or not is p-val. So including this check here, and since this is basically assuming that index has some meaningful indexes, it will get rid of the other ones or the false ones, it will just get the true ones. This is basically the elimination part, this is the determination part. So I can copy and paste it and use p-val positive, and that's it. Now, let's see what happens then. If we look for p-val, we have two values. Now, if I run it again, we have just one value, one k-val, one omega n val, and that's it. So we can, again, uncomment this part to see what's really happening. Now, also, since I don't have any settling time, plotting this line here does not make that much sense. Maybe what I can do is I can just plug in ones here because, so let's have that, because zeta equals 1 for this case or instant should be equal to this one here, but I don't know what omega n is because they will coincide on omega n. So maybe it's a good idea to get rid of this line. So there's no settling time line, therefore. So there we go. Let's see. Now, as expected, we are on the real axis here. And you can see, since the root locus is underneath the poles here, we can see that one of the poles at -5 and the other one at the origin did approach this point and they met here. And then we have also a third pole here. So 2 on -2 and then 1 here somewhere. And you can also see that there's no overshoot. This looks like a response of a first order transfer function. And we have a certain settling time here. Of course, we didn't choose the settling time here. Therefore, it doesn't really matter that much. And the distance is also not that big anymore. It was approximately 6 for round 2, so for 2.5 seconds, and then was it 11 or something for the first part. Here we have 4.5, but since the requirement only is about zeta being equal to 1 or 0 overshoot, it does satisfy it. Yeah, it's basically it, because we were looking for zeta equals 1. For such a controller to exist, the only thing is that we should have a breakpoint here, breakaway point here. And that's basically it, because we're choosing that point. You can also maybe use the root locus on its own. If you click in on the root locus, you can immediately see that using gain 36 is the solution. By the way, you can use R locus and click on R locus and choose your controller from there. But it doesn't mean that you would get the exact design, because here when you see a certain damping ratio, that's not the damping ratio of the whole system. That's only the damping ratio of these 2 poles. If I, for example, click on here, I have a different damping ratio, which is equal to 1. So don't misinterpret this interface here. This damping ratio does mean that the damping ratio is associated with these 2 poles, only these 2 poles. This doesn't mean that the closed loop will have this damping ratio. Okay? If we have, for example, a 4th order system, there might be 2 different damping ratios because of 2 different complex conjugate poles. Now, so the last part here tells us to design a controller for 1.5 seconds. And unuttum, evet ya. Şunu verebilir miyim? Now, the design was TS equals 4, TS equals 2.5, and then we looked at critical damp. And then for some reason, we have again TS equals 1.5. So this should look a little bit suspicious. Let's see if it is or if it's not. So there we go. I've basically copied and pasted it, and I'm going to plug in 1.5. So interestingly, even though I've plugged in the settling time value, the code here didn't find me a solution. So let's see what the problem is. Now, if you look closer here, you can see that there's a certain p-value. I can calculate the value of p. And if I have that p-value, I can go ahead and calculate this, take the difference, and then take the square root of this. And then if I know p and omega n, I should be able to calculate a certain k value. So what could be the problem here? Because for some reason it didn't work. And if I look into the solution, I can see that it's not about my elimination piece here, where I was looking for positive omega n or positive p-value, etc. We don't get any solution here. So how about that? Well, the reason that there's no solution is the following. If we calculate the value of p, 5.333, it is 7.66. And if we calculate this multiplication, you can see that this is 40.88. And here we have 40. Now, in this case, in order to satisfy the third equation here, omega n squared should be negative. Otherwise, I'm not able to satisfy this condition. And if omega n squared is negative, that means that the square root will be negative 1 or minus 1, which means that omega n should be complex. And I'm not allowing it. So if you go ahead and get rid of this real keyword here, that means that omega n can be complex now. And if I run this twice on my computer, let's look at the solution. And we have two different solutions. And guess what? These are imaginary. If we look at omega n, well, due to the elimination, I'm not able to see them. So let's get rid of this here, basically. You can see that there are complex conjugate values. And it is equal to 0.9428. So, what does this mean? By definition, omega n and zeta should be real values and positive real values. What happens if I suddenly end up with an imaginary number or value or complex value? Well, let's, for example, choose one of them. So instead of having this, let me just say, take just the first solution here. And we end up in this. So what is the issue? First of all, we have p-val. This is 7.66. So it shouldn't be really a big of a deal, even though my ratio is not that high. Now, if I have omega n, let me zoom in a little bit more. I can see that basically one of my poles is on the right-hand side, right half plane. Therefore, it's not stable. So if I look at ZPK TS, I get this. So 0.16 on the right half plane means instability. But I also see that my K value, my controller is negative, which means that I'm on the negative root locus, not on the positive one. And you can see that here, obviously. It's not on the branches. It is on the negative one because they approach each other and then the breaking point is here, etc. But the main focus here is here. Now, for the positive root locus, I can see that only one pole can be on this settling time line, namely the green one here. So, for example, if I click on this, the numerical problem here is I cannot click exactly here, but let's assume that this is almost there. So I can choose, for example, gain 30, and one of the poles can be on this line, but the other one is not. So remember that I need to have complex conjugate poles in order to be able to use the settling time formula. So zeta should be between 0 and 1. That means that both of the poles, of the dominant poles, should be on this line. Now, on the positive root locus, that doesn't happen. For the previous examples, that was always the case, but here it's not. But what I can do is I can look for the negative root locus by just including a negative sign here, minus sign here. Here, we still have a problem because now it's still not on the root locus. So basically, the settling time value that I've chosen here, 1.5, cannot be achieved using this p-type controller because the first condition is to be on the root locus. So if the point that I'm trying to choose here is not on the root locus, how can I come up with a p-type controller that satisfies that point? It should be first on the root locus. So the root locus plot is basically the limitation on the choice of poles. If there's a root locus plot, that means that only the path of the root locus is your candidate pole family. So in other words, it means that you can only choose the points drawn by the root locus plot and nothing else. So you're not free, basically. And I've talked about the fact that we have this denominator here, and we are only affecting this polynomial by this constant term. So that's the trade-off here. If you only change the constant term here, then you can only move on the root locus here. So let me show you the positive one. If you only can change the constant term, then for positive k values, you're on this root locus. For negative ones, you're on the negative root locus, and that's it. Therefore, using a p-type controller, I cannot design a p-type controller that ends up in settling time 1.5 because I'm not on the root locus plot. So this shows me that for this system especially, I have a natural settling time limit because lower settling times means faster response, but the system cannot perform at that speed for this system especially. So therefore, there are two ways that can solve this problem. One of them being changing the settling time requirement because you want too much of a p-type controller for the system. It has a stable closed loop and it can reach certain levels of settling time, and that's it. It cannot do much because of this limitation. If you're free to choose all the coefficients of this, or if you're affecting all the coefficients of this polynomial, then you are basically able to do anything to this system. Choose any rise time, settling time, overshoot whatsoever. But if you have just this constant term, then that's basically it. And the other solution would be to choose a different controller. Maybe a controller that has more freedom here, because this p-type controller can only affect this constant term. Maybe there's a controller like a PD controller, for example, that can also affect this S term here. Maybe that's helping. So the translation to root locus of that would be to add some extra poles and zeros to the root locus, because the only way you can change the root locus plot is to add some poles or zeros to it. So if I add, for example, a 0 here, then it will bend this root locus to the left, and maybe it will pass through this settling time line. So therefore, for such occasions, you have to somehow affect the root locus itself and then choose a p-type controller. That will be basically the controllers that we address in the upcoming weeks. But for the p-type controller, there does not exist a controller that can result in a settling time 1.5. And the reason behind that is, one is the fact that omega n is not real in the coefficient method here, or the algebraic method, as we call it. Here, omega n is not real, so there's no solution that omega n is real. Therefore, we cannot design such a controller. Or if you look at the root locus, we can see and conclude that it's not on the root locus, therefore it's not achievable. So that's pretty much important. Now, let's look at the notes and conclude today's discussion here. So yeah, there are all the steps necessary in order to follow along. We have 4 divided by zeta omega n, and then this is our desired polynomial. So let me repeat this. I can only define a second-order polynomial that has the time characteristics that I'm interested in. And if I have a higher order system, then I'm adding just the difference there. If I have a 4th order, I'm adding 2 poles to it. And I'm basically trying to have them as far on the left, on the S-plane as possible. And I also want them to be on the left half plane because stable closed loop. Therefore, I'm adding some poles. I'm calculating the desired closed loop or the model that I have. And then there's also the part where I have the controller and the feedback loop. I calculate the characteristic polynomial of that, and I try to equate the coefficients. This gives me a set of equations, and I try to solve it. Once I've solved it, I'm going to verify them. I have to plug in all the values that I've calculated, and I have to see if my strategy is correct, if it's working. Now, for the first case, we had a high k value, a gain value, and also the dominance factor here, which determines if our responses or strategy works or not. The ratio there was good, so the distance was sufficient. Therefore, we had a working solution. But the solution had less zeta value, which meant that we would have more overshoot. And then for a different settling time value, we ended up in a better, in a lower k value, in a lower dominance factor, but in terms of overshoot or zeta, we had a less overshoot value or response here. And then we tried zeta equals 1, which has basically 0 overshoot, since all the poles are on the real axis, and you can see that the resulting closed loop looks like this. So 2 on s equals -2, and then 1 on -9, and the ratio is 4.5 basically. But since this is only a critically damped solution, it's basically already a good one. And then we had 1.5, which then ended up being not on the settling time line here. Therefore, we were not able to choose such a controller. So that's basically it for this week. What we've done is we've attacked the p-type controller design problem a bit. Today, we've talked about second-order system transients today, namely the settling time overshoot properties. And in the upcoming weeks, we will again continue on this discussion, continue on how to design controllers. That's basically it for today. Now, to remind you of the fact that I've used the algebraic method where we use the polynomial coefficients to determine the exact values to attack the problem from one side. And I've also used the root locus method to analyze my solutions and attack the problem from a different perspective. Therefore, you have to know that you need to use both methods simultaneously, because one of them is showing some perspective and the other one is completing the picture. So that's basically it for today. If you have any questions, feel free to ask. If not, I'll be seeing you in the next session.